So we have some examples where we're trying to apply the idea of what it means to react in a thermodynamically favorable way. A word that used to be used to describe this, and you'll still see in a lot of online resources and textbooks, is spontaneously. Spontaneously means happens without the need of outside energy, which is exactly what we're talking about with thermodynamically favorable. The problem is that word has kind of been used to mean quickly, and that's not what we're talking about here. We'll see kinetics is totally separate. But if we're talking about this, ice at room temperature spontaneously melts in water. Doesn't mean instantaneously, it just means it happens without us needing to force that to occur. But in terms of enthalpy and entropy, we have to think of that. From an enthalpy sense, melting is endothermic. It requires outside energy. That's actually unfavorable for ice to melt. But from an entropy sense, when we are changing from a solid to a liquid, we do have an increase in randomness. We do have more disorder, and that is favorable from the entropy sense. So overall, we know that that occurs, and it is thermodynamically favorable, or it will occur without the input of extra energy from the outside, because in that circumstance, there is a high enough temperature that enthalpy piece, the melting piece, can occur. It can absorb the necessary energy, and it also has the entropy. So entropy technically drives the reaction. That's the more favorable part of it. But at the temperature we're at room temperature, above the melting point, there is enough heat to also think of this in terms of enthalpy. Our second example of a candle burning is a good example of something that is favorable from a thermodynamic sense in every way. So we have solid wax, that's a whole bunch of carbons and hydrogens together. We have oxygen gas. We could write this out and balance it to think of it in terms of moles, but really the state of matter is the main thing we're looking at. A solid reacting with a gas, producing gaseous CO2, and water vapor, a gas. So in terms of enthalpy and entropy, from an enthalpy sense, all burning or all combustion reactions release energy and are exothermic, meaning we don't have to absorb anything from the surroundings. The energy flows from system to the surroundings. That is favorable. From an entropy sense, we do start with something that is a solid and one gaseous component. Everything that we make in terms of products is gaseous. So we are going from a very orderly solid to very random gases. That increases the randomness of our system. Both of these are favorable, and that reaction would be driven by both. But if we go back to the word spontaneously, that doesn't mean that the candle instantaneously melts or burns, or that the candle can start on its own. It just means that process, as it starts, is a favorable process from a thermodynamic sense. Coming down to C, ammonium nitrate is a solid. Sometimes we use this in class in regular honors or AP chemistry for a lab. It looks like tiny little Dippin' Dots, which is interesting because it actually, when it reacts or dissolves in water, it makes it very, very cold. So we use that in those instant cold packs, not the ones you put in the freezer, but the ones that you kind of pop and then shake up, because it makes the temperature drop a lot. When this dissolves, the temperature drops. So let's think about that in terms of enthalpy and entropy. For enthalpy, that is an endothermic process. The temperature dropping proves that it's absorbing energy from the water, from the air, from the package, from our hands, in fact. So there has to be enough energy in the surroundings for this to occur, and that's actually unfavorable. It can only occur when that energy is flowing in. But from an entropy sense, we had a pure solid, and inside of the package, it was separate from the water, and a pure liquid, and then we made a solution out of those. We have mixed them up and made them much more random. We have much more disorder. Instead of having a nice orderly solid and a pure liquid as they are mixed. So overall, it is thermodynamically favorable. And we can say that because when you pop it, something happens. It changes. That's kind of our big sign for delta G. If something occurs chemically or physically, that means it's favorable under its current conditions, which means there's enough temperature or heat in the surroundings in general that this can occur. But the entropy itself is the favorable part. Entropy, or that randomness, is always going to make this more favorable, whereas from a heat sense, it's only going to work if it's hot enough, which does lead us into question B. We had three scenarios, and when we looked at B, it was exothermic. That's good in terms of thermo, and it increased entropy, which was good. So no matter how hot or how cold I make that, that process would be favorable and would occur as soon as we started it. But A and C are not always favorable. We can definitely think about this in terms of the equation. If I want a negative delta G, I know the value of delta H maybe. In both of those cases, it was positive. Only when my T delta S is big enough does that make my delta G negative. Both of these instances occurred and would occur probably at room temperature. So that means whatever temperature we think of, maybe that 298 Kelvin standard temperature, is big enough to make the entropy value significantly large enough that delta G ends up negative. So we can do that. Or right here, these become more favorable as temperature increases. We can think of that in terms of melting quite easily. The hotter it gets, the more likely it melts. And that's because there is more energy available to be absorbed from the surroundings. This is true as well. The hotter it is, the faster that reaction can occur. It won't necessarily make our cold pack colder, but the process can occur more quickly. They require that input of energy from the surroundings, from the outside source. So the hotter those surroundings are, from a thermodynamic sense, they become more favorable. And we also want to be really comfortable kind of transitioning to the next idea that we can apply this with math. The bigger this value is, the more negative that one becomes.